So today we're going to start our discussion of calculus as it relates to the area. Now, in calculus they call it area under the curve. We talked about this before. Area under the curve isn't a great way to say this, but it's really useful for us as long as we know what we're talking about. So let's see what it looks like. In our discussions from the other day, what we realized was that if we were to look at position, velocity, and acceleration graphs, what we would see is that depending on the scenario of the situation, let's say we go with our standard situation here. These graphs all have shapes we're familiar with. Position is a parabola. Velocity is linear. Acceleration is horizontal. We know that if you look from here to here, oh my God. If you analyze the slope of the position, you get the velocity. Analyze the slope of the velocity, you get the acceleration values. For example, the slope of that is constant positive, so our velocity or our acceleration value is constant and positive. But what we realized the other day is you can go back the other direction. What if we go back the other direction? If you examine the area here, you can get some information about the velocity. If I were to drop this down and shade this area, that area would be the change in velocity. Same thing here. I can go back the other direction. If I examine the area, that area is the change in position. We call that the displacement. This is really easy to do if, for example, your shape is regular. Like this is either a trapezoid, or you can break it up into a rectangle and a triangle, and you can just add the areas up, no big deal. But that brings us to the hard question. And the hard question is, what if I had a velocity versus time graph, and I wanted to find the change in position, but the velocity versus time graph wasn't linear? What would I do then? Well, let's see how it looks. What if I had a velocity versus time graph that was, for example, a big parabola? Is there a way for us to figure out the area? Now we call area under the curve, but in this case, it's the area between your line and the horizontal axis. Is there a way to do that in a way that's meaningful? That's a great question. Let's see if we can't figure it out. So given this construct, what I see here is that I need to get this area. So one of the ways we think about this is we think about, well, okay, well, if this is the area here, I'm going to drop this down, I'm going to see if I can shade, but this isn't a regular shape, and I don't know how to do that. Frankly, I'm not that smart, so the only thing I know how to do is figure out the area of a rectangle anyway. So let's see what this looks like. That's the time. That's the velocity. So over time, it looks like our object starts with 0 velocity, and over time it speeds up, and at time t it has velocity there. So if I wanted to find the area, I could look at this rectangle, for example, and I know the area is the displacement. Let's write that down. And how would I solve for this? Well, I would take the area of this rectangle, it's t wide and v tall, so the area here is equal to vt. But this is kind of bad because I'm calculating this whole area here, but the area I want is just the area beneath the curve, between the curve and the horizontal axis, which means I have all this stuff up here, which is not the area, but it's calculated in here. So we call that the error. How can we minimize our error is the question. Well, one way to do that is to take my t, and what if I broke it up into 2t sections? Okay, so let's break it up in half. Now we'll call this one t1, this one t2. Have to call that v1, velocity at time 1, and velocity at time 2. So this is one rectangle here, and this is another rectangle over here. So what I have is I have now two rectangles instead of one large one, and I've reduced my amount of error by taking out this amount right here. This is better, but I still have all this and all this, which are kind of, outside of what I'm actually looking for. But it's better. And so here's what we say now. So I get my, oh, that's not right, because this is v1 times t1, but t2 is this whole distance here. So that's not the right statement at all. Is there a way for us to amend our statement here? Well, one thing I can notice is if I look, that's like a delta t, that's the time interval between 1 and 2, but since I broke this in half, that's also the time interval between 0 and 1. So what I actually have is the width of this rectangle is delta t, and the height is v1. This width is delta t, the height is v2. So let me amend this statement. To list the areas of these two rectangles, it's v1 times delta t plus v2 times delta t. So that makes more sense to me now, okay? But the problem is we still have a ton of error in these two large sections. Is there a way for us to reduce the error? Well, the last thing we did was we broke our t sections up into smaller delta t sections. Let's see if we can't do that again. I'm going to take my t1 and break it up into two sections. Take my t2 and break it up into two sections. Now what I have is I have a new t1, new t2, t3, and t4. That's my new v1, v2, v3, and that one is now v4. So what does my new area picture look like? Well, so now I have 1, 2, 3, 4 rectangles, and they're much smaller width. What happened to my delta t here? My delta t is half what it was in the previous delta t, and what I'm noticing here is I have less and less error than I did the last time, which is good. How would I express all of the areas together? Now, it's a little tedious to write them all. It's a little tedious to write them all. I wonder if there's a way for us to express something if I want to add them all up. Turns out there is. It's a Greek letter. It's called sigma. And sigma tells you to add up the sum of all these things. So let me write it in sigma notation. Sigma means add them up. What am I adding up? Well, I'm adding up v delta t, but what v's? Well, let's just say I is a variable. So this notation says, as I goes from 1 to 4, add up v1 times delta t plus v2 times delta t plus v3 times delta t plus v4 times delta t. So these two lines are equivalent. This one's just a shorter notation for writing it, which I think is cool. Unfortunately, if you notice, I still have a good deal of error there. So what am I going to do? I'm going to do what I did before, and I'm going to take my delta t and I'm going to shrink it by a factor of 2 again. We now have 8 times. My delta t is half of what it was the previous time. If I come over here, so I have 8 times across the bottom, 8 velocities across the top. Let's see if we can't figure out what the area picture looks like. This is much smoother now. I have smaller rectangles, but they're half the width, but there's twice as many of them. But the amount of error is getting smaller and smaller. But what does the notation look like for this one? But now I have twice as many things to add up. My I is going from 1 to 8 because I now have rectangles. They all have the same width though, the VI times the delta t. I could do this again. I could say, well, I'm going to double the amount of times. I could go half the delta t again. I'd have 16 times and 16 velocities. This would go from 1 to 16. I'm still going to be left with amount of area. So how can we really minimize, right? How can we really minimize the amount of error? What would have to happen to my delta t in order for this thing to get shrunk down so that we have almost no, or really until we have no area? This is like something we did before, and what would have to happen was that my delta t value would have to go to 0. I'd have to shrink the delta t down until it was close to 0, which is cool, except for here's my issue. If I make delta t go to 0, I'm multiplying everything by 0, and then I have no area, which we know doesn't make any sense at all, because I have all this area underneath here. So we're going to employ the same concept that we did before, is we don't really want it to go to 0 to make it equal to 0. We want it to go towards 0. So we have this same concept. We call it the limit. But here's the problem. What goes here? Like, if I'm going to shrink this down so it's getting closer and closer to 0, what's happening to my actual number of rectangles themselves? Every time I half this, I double the number of rectangles. If I half it again, I double the number of rectangles. So making this smaller makes the number of rectangles go up. If I make this infinitely small, it means my number of rectangles has to be infinitely large. And that's how I write it. When we're taking the limit, as delta t goes to 0, my number of rectangles goes from 1 to infinity. It goes from 1 to infinity. And that's what I really like about this, is it gives us a sense of what would happen. The issue is we can't actually really do it, okay? So here's how we roll from here. If we're taking the limit, as the delta t goes to 0, we know we can't do it here, right? It can't really be 0, but we're taking the limit. We can't really add up an infinite number of an infinite number of rectangles either. So here's what we're going to do. We're going to take my sigma, I'm going to grab one end with this hand, we're going to grab one end with this hand, and we're going to stretch it out, and we end up with a new symbol. We get this elongated s, it turned in from a sigma to this elongated s. It implies 0 to infinity of v dt. So